For the last problem dealing with torque, we have number 10. This is a double star problem, so it's going to be a little bit, probably involve a system of equation. So it says a rotational axis is directed perpendicular to the plane of a square and is located as shown in the drawing. Two forces, F1 and F2, are applied to diagonal opposite corners and act along the sides of the square, first as shown in part A and then as shown in part B of the drawing. In each case, the net torque produced by the forces is 0. The square is 1 meter on a side, and the magnitude F2 is 3 times that of F1. Find the distance A and B that are locate the axis. Okay, so they want us to find the axis of rotation of this square. Now, even though in the picture it looks like it's exactly in the middle, it is not. What we have to work with is the fact that they also told us the square is 1 meter. They also told us that the F2 is 3 times larger than the F1, and you can even see it on the picture because they actually drew the arrows much greater. And for part A, if we start looking for part A, they tell us that the net torque is 0. That means the torque created by the F2 and F1 have to cancel out. So F2, which is a force acting in the y direction, has an x displacement from the axis of equal to A. We don't know what A is. We don't have to take into B into account because B acts in the y and there's no F2 has no x component, so it doesn't need the y displacement. And we're going to make it negative because the torque that's going to make it rotate clockwise. F1 is located a B distance below the axis, and that's going to have a positive rotation. So we can clean up our equation a bit. So F2A is equal to F1B, and if we substitute the fact that F2 is equal to 3 times that of F1, we can write that equation in terms of F1. You can cancel out the F1s, and we find out that B the displacement B is 3 times greater than the displacement A. But again, we have two unknowns, so we're going to need another equation, which is why we look at part B. For part B, we again have the same forces F1 and F2, just acting at different positions. Now, we cannot assume that the displacement from the center of axis in the x direction to F1 is A, because the actual center of axis may not actually be in the center of the square. It might be off, like it's a hinge. Don't get it confused with center of mass. So instead of, since we don't know the distance, but we do know that the entire length of the square is 1, so that means the distance from the axis to where F1 is 1 minus A, and the distance to F2 is just the B. And the F1 force is going to cause a positive rotation, the F2 force is going to cause a negative rotation. And then we clean up the equation, we found out that F2B is equal to F1 1 minus A, and we could distribute it, but we didn't really need to distribute it because when we do the substitution again, the fact that F2 is 3 times larger than F1, and we end up having to cross out the F1s anyway, so we didn't really have to distribute, we just had to substitute the F2. Then we get the equation 3B is equal to 1 minus A. We kind of combine those equations using systems of equations. We substitute 3A into B from the second equation we got, and then we get 9A equals 1 minus A, and we solved through it, and we found out that A is equal to 1/10 of a meter, which means B has to equal 3/10 of a meter. And once we plug it back into that 3A equals B equation, and that gives us our values. So the axis is actually much closer to the right, because it's only 1/10 of a meter to the left, and it's 3/10 of a meter above it. So it's going to be, maybe if we actually looked at the circle, the actual rotation would probably end up being somewhere like there, if we were drawing the scale. Actually, sorry, that's way too high. It should be somewhere around there, very much closer to the corner.